Engineering drawing.
An engineering drawing, a type of technical drawing, is used to fully and clearly define requirements for engineered items. Engineering drawing, the activity, produces engineering drawings, the documents. More than just the drawing of pictures, it is also a language, a graphical language that communicates ideas and information from one mind to another. Most especially, it communicates all needed information from the engineer who designed a part to the workers who will make it.
Overview. Relationship to artistic drawing.
Engineering drawing and artistic drawing are both types of drawing, and either may be called simply drawing, when the context is implicit. Engineering drawing shares some traits with artistic drawing in that both create pictures. But whereas the purpose of artistic drawing is to convey emotion or artistic sensitivity in some way, subjective impressions, the purpose of engineering drawing is to convey information, objective facts. One of the corollaries that follows from this fact is that, whereas anyone can appreciate artistic drawing, even if each viewer has his own unique appreciation, engineering drawing requires some training to understand, like any language. But there is also a high degree of objective commonality in the interpretation, also like other languages. In fact, engineering drawing has evolved into a language that is more precise and unambiguous than natural languages. In this sense it is closer to a programming language in its communication ability. Engineering drawing uses an extensive set of conventions to convey information very precisely, with very little ambiguity.
Relationship to other technical drawing types.
The process of producing engineering drawings, and the skill of producing those, is often referred to as technical drawing or drafting, also spelled drafting, although technical drawings are also required for disciplines that would not ordinarily be thought of as parts of engineering, such as architecture, landscaping, cabinet making, and garment making.
Cascading of conventions by specialty.
The various fields share many common conventions of drawing, while also having some field-specific conventions. For example, even within metalworking, there are some process-specific conventions to be learned. Casting, machining, fabricating, and assembly all have some special drawing conventions, and within fabrication there is further division, including welding, riveting, pipe fitting, and erecting. Each of these trades has some details that only specialists will have memorized.
Legal instruments.
An engineering drawing is a legal document, that is, a legal instrument, because it communicates all the needed information about what is wanted of the people who will expend resources turning the idea into a reality. It is thus a part of a contract. The purchase order and the drawing together, as well as any ancillary documents, engineering change orders, called out specs, constitute the contract. Thus, if the resulting product is wrong, the worker or manufacturer are protected from liability as long as they have faithfully executed the instructions conveyed by the drawing. If those instructions were wrong, it is the fault of the engineer. Because manufacturing and construction are typically very expensive processes, involving large amounts of capital and payroll, the question of liability for errors has great legal implications as each party tries to blame the other and assign the wasted cost to the other's responsibility. This is the biggest reason why the conventions of engineering drawing have evolved over the decades toward a very precise, unambiguous state.
Standardization and disambiguation.
In service of the goal of unambiguous communication, engineering drawings are often made professionally and expected to follow certain national and international standards, such as ASME Y14.5 and Y14.5M, most recently revised in 2009, or a group of ISO standards with similar content. Standardization also aids with internationalization, because people from different countries who speak different languages can share the common language of engineering drawing, and can thus communicate with each other quite well, at least as concerns the geometry of an object.
Media.
For centuries, until the post-World War II era, all engineering drawing was done manually by using pencil and pen on paper or other substrate, for example, vellum, mylar. Since the advent of computer-aided design, CAD, engineering drawing has been done more and more in the electronic medium with each passing decade. Today most engineering drawing is done with CAD, but pencil and paper have not disappeared. Some of the tools of manual drafting include pencils, pens and their ink, straight edges, T-squares, French curves, triangles, rulers, protractors, dividers, compasses, scales, erasers, and tacks or push pins. Slide rules used to number among the supplies too, but nowadays even manual drafting, when it occurs, benefits from a pocket calculator or its on-screen equivalent. And of course the tools also include drawing boards, drafting boards, or tables. The English idiom to go back to the drawing board, which is a figurative phrase meaning to rethink something altogether, was inspired by the literal act of discovering design errors during production and returning to a drawing board to revise the engineering drawing. Drafting machines are devices that aid manual drafting by combining drawing boards, straight edges, pantographs, and other tools into one integrated drawing environment. CAD provides their virtual equivalents. Producing drawings usually involves creating an original that is then reproduced, generating multiple copies to be distributed to the shop floor, vendors, company archives, and so on. The classic reproduction methods involved blue and white appearances, whether white on blue or blue on white, which is why engineering drawings were long called, and even today are still often called, blueprints, or bluelins, even though those terms are anachronistic from a literal perspective, since most copies of engineering drawings today are made by more modern methods, often inkjet or laser printing, that yield black or multicolor lines on white paper. The more generic term print is now in common usage in the US to mean any paper copy of an engineering drawing. In the case of CAD drawings, the original is the CAD file, and the printouts of that file are the prints.
Relationship to model-based definition (MBD-DPD).
For centuries, engineering drawing was the sole method of transferring information from design into manufacture. In recent decades another method has arisen, called model-based definition, MBD, or digital product definition, DPD. In MBD, the information captured by the CAD software app is fed automatically into a CAM app, computer-aided manufacturing, and is translated via post-processor into other languages such as G-code, which is executed by a CNC machine tool, computer numerical control. Thus today it is often the case that the information travels from the mind of the designer into the manufactured component without having ever been codified by an engineering drawing. In MBD, the dataset, not a drawing, is the legal instrument. The term technical data package, TDP, is now used to refer to the complete package of information, in one medium or another, that communicates information from design to production, such as 3D model datasets, engineering drawings, engineering change orders, ECOs, spec revisions and addenda, and so on. However, even in the MBD era, where theoretically production could happen without any drawings or humans at all, it is still the case that drawings and humans are involved. It still takes CAD CAM programmers, CNC setup workers, and CNC operators to do manufacturing, as well as other people such as quality assurance staff, inspectors, and logistics staff, for materials handling, shipping and receiving, and front office functions. These workers often use drawings in the course of their work that have been produced by rendering and plotting, printing, from the MBD dataset. When proper procedures are being followed, a clear chain of precedence is always documented, such that when a person looks at a drawing, he is told by a note thereon that this drawing is not the governing instrument, because the MBD dataset is. In these cases, the drawing is still a useful document, although legally it is classified as for reference only, meaning that if any controversies or discrepancies arise, it is the MBD dataset, not the drawing, that governs.
Systems of dimensioning and tolerancing.
Almost all engineering drawings, except perhaps reference-only views or initial sketches, communicate not only geometry, shape and location, but also dimensions and tolerances for those characteristics. several systems of dimensioning and tolerancing have evolved. The simplest dimensioning system just specifies distances between points, such as an object's length or width, or whole center locations. Since the advent of well-developed interchangeable manufacture, these distances have been accompanied by tolerances of the plus or minus or min and max limit types. Coordinate dimensioning involves defining all points, lines, planes, and profiles in terms of Cartesian coordinates, with a common origin. Coordinate dimensioning was the sole best option until the post-World War II era saw the development of geometric dimensioning and tolerancing, GD&T, which departs from the limitations of coordinate dimensioning, for example, rectangular-only tolerance zones, tolerance stacking, to allow the most logical tolerancing of both geometry and dimensions, that is, both form and sizes.
Engineering drawings, common features.
Drawings convey the following critical information. Geometry, the shape of the object. Represented as views. How the object will look when it is viewed from various angles, such as front, top, side, etc. Dimensions, the size of the object is captured in accepted units. Tolerances, the allowable variations for each dimension. Material, represents what the item is made of. Finish, specifies the surface quality of the item, functional or cosmetic. For example, a mass-marketed product usually requires a much higher surface quality than, say, a component that goes inside industrial machinery.
Line styles and types.
A variety of line styles graphically represent physical objects. Types of lines include the following. Visible, are continuous lines used to depict edges directly visible from a particular angle. Hidden, are short dashed lines that may be used to represent edges that are not directly visible. Center, are alternately long and short dashed lines that may be used to represent the axes of circular features. Cutting plane, are thin, medium dashed lines, or thick alternately long and double short dashed that may be used to define sections for section views. Section, are thin lines in a pattern determined by the material being cut, or sectioned used to indicate surfaces in section views resulting from cutting. Section lines are commonly referred to as cross-hatching. Phantom, not shown, are alternately long and double short dashed thin lines used to represent a feature or component that is not part of the specified part or assembly. For example, billet ends that may be used for testing, or the machine product that is the focus of a tooling drawing. Lines can also be classified by a letter classification in which each line is given a letter. Type A lines show the outline of the feature of an object. They are the thickest lines on a drawing and done with a pencil softer than HB. Type B lines are dimension lines and are used for dimensioning, projecting, extending, or leaders. A harder pencil should be used, such as a 2 hours. Type C lines are used for breaks when the whole object is not shown. These are freehand drawn and only for short breaks. 2 hours pencil. Type D lines are similar to Type C, except these are zigzagged and only for longer breaks. 2 hours pencil. Type E lines indicate hidden outlines of internal features of an object. These are dotted lines. 2 hours pencil. Type F lines are Type F lines, except these are used for drawings in electrotechnology. 2 hours pencil. Type G lines are used for center lines. These are dotted lines, but a long line of 10 to 20 mm, then a gap, then a small line of 2 mm. 2 hours pencil. Type H lines are the same as Type G, except that every second long line is thicker. These indicate the cutting plane of an object. 2 hours pencil. Type K lines indicate the alternate positions of an object and the line taken by that object. These are drawn with a long line of 10 to 20 mm, then a small gap, then a small line of 2 mm, then a gap, then another small line. 2 hours pencil.
Multiple views and projections.
In most cases, a single view is not sufficient to show all necessary features, and several views are used. Types of views include the following.
Orthographic projection.
The orthographic projection shows the object as it looks from the front, right, left, top, bottom, or back, and are typically positioned relative to each other according to the rules of either first-angle or third-angle projection. The origin and vector direction of the projectors, also called projection lines, differs, as explained below. In first-angle projection, the projectors originate as if radiated from a viewer's eyeballs and shoot through the 3D object to project a 2D image onto the plane behind it. The 3D object is projected into 2D paper space as if you were looking at a radiograph of the object. The top view is under the front view, the right view is at the left of the front view. First-angle projection is the ISO standard and is primarily used in Europe. In third-angle projection, the projectors originate as if radiated from the 3D object itself and shoot away from the 3D object to project a 2D image onto the plane in front of it. The views of the 3D object are like the panels of a box that envelopes the object, and the panels pivot as they open up flat into the plane of the drawing. Thus the left view is placed on the left and the top view on the top. And the features closest to the front of the 3D object will appear closest to the front view in the drawing. Third-angle projection is primarily used in the United States and Canada, where it is the default projection system according to British Standard BS 8888 and ASME Standard ASME Y14.3M. Until the late 19th century, first-angle projection was the norm in North America as well as Europe. But circa the 1890s, the meme of third-angle projection spread throughout the North American engineering and manufacturing communities to the point of becoming a widely followed convention, and it was an ASA standard by the 1950s. Circa World War I, British practice was frequently mixing the use of both projection methods. As shown above, the determination of what surface constitutes the front, back, top, and bottom varies depending on the projection method used. Not all views are necessarily used. Generally only as many views are used as are necessary to convey all needed information clearly and economically. The front, top, and right side views are commonly considered the core group of views included by default, but any combination of views may be used depending on the needs of a particular design. In addition to the 6 principal views, front, back, top, bottom, right side, left side, any auxiliary views or sections may be included as serve the purposes of part definition and its communication. View lines or section lines, lines with arrows marked AA, BB, etc. define the direction and location of viewing or sectioning. Sometimes a note tells the reader in which zone, S, of the drawing to find the view or section.
Auxiliary projection.
An auxiliary view is an orthographic view that is projected into any plane other than one of the 6 principal views. These views are typically used when an object contains some sort of inclined plane. Using the auxiliary view allows for that inclined plane, and any other significant features, to be projected in their true size and shape. The true size and shape of any feature in an engineering drawing can only be known when the line of sight, LOS, is perpendicular to the plane being referenced. It is shown like a 3-dimensional object.
Isometric projection.
The isometric projections show the object from angles in which the scales along each axis of the object are equal. Isometric projection corresponds to rotation of the object by ± 45 deg about the vertical axis, followed by rotation of approximately ± 35.264 deg about the horizontal axis starting from an orthographic projection view. Isometric comes from the Greek for same measure. One of the things that makes isometric drawings so attractive is the ease with which 60-degree angles can be constructed with only a compass and straight. Isometric projection is a type of axonometric projection. The other 2 types of axonometric projection are dimetric projection, trimetric projection.
Oblique projection.
An oblique projection is a simple type of graphical projection used for producing pictorial, 2-dimensional images of 3-dimensional objects. It projects an image by intersecting parallel rays, projectors, from the 3-dimensional source object with the drawing surface, projection plan. In both oblique projection and orthographic projection, parallel lines of the source object produce parallel lines in the projected image.
Perspective.
perspective is an approximate representation on a flat surface of an image as it is perceived by the eye. The two most characteristic features of perspective are that objects are drawn smaller as their distance from the observer increases. Foreshortened, the size of an object's dimensions along the line of sight are relatively shorter than dimensions across the line of sight.
Section views.
Projected views, either auxiliary or orthographic, which show a cross-section of the source object along the specified cut plane. These views are commonly used to show internal features with more clarity than may be available using regular projections or hidden lines. In assembly drawings, hardware components, for example nuts, screws, washers, are typically not sectioned.
Scale.
Plans are usually scale drawings, meaning that the plans are drawn at specific ratio relative to the actual size of the place or object. Various scales may be used for different drawings in a set. For example, a floor plan may be drawn at 150, 148 or 1/4 equals 1-0, whereas a detailed view may be drawn at 125, 124 or 1/2 equals 1-0. Site plans are often drawn at 1/200 or 1/100. Scale is a nuanced subject in the use of engineering drawings. On one hand, it is a general principle of engineering drawings that they are projected using standardized, mathematically certain projection methods and rules. Thus, great effort is put into having an engineering drawing accurately depict size, shape, form, aspect ratios between features, and so on. And yet, on the other hand, there is another general principle of engineering drawing that nearly diametrically opposes all this effort and intent, that is, the principle that users are not to scale the drawing to infer a dimension not labeled. This stern admonition is often repeated on drawings, via a boilerplate note in the title block telling the user, "Do not scale drawing." The explanation for why these two nearly opposite principles can coexist is as follows. The first principle, that drawings will be made so carefully and accurately, serves the prime goal of why engineering drawing even exists, which is successfully communicating part definition and acceptance criteria, including, what the part should look like if you've made it correctly. The service of this goal is what creates a drawing that one even could scale and get an accurate dimension thereby. And thus the great temptation to do so, when a dimension is wanted but was not labeled. The second principle, that even though scaling the drawing will usually work, one should nevertheless never do it, serves several goals, such as enforcing total clarity regarding who has authority to discern design intent, and preventing erroneous scaling of a drawing that was never drawn to scale to begin with, which is typically labeled drawing not to scale, or scale, NTS. When a user is forbidden from scaling the drawing, he must turn instead to the engineer, for the answers that the scaling would seek, and he will never erroneously scale something that is inherently unable to be accurately scaled. But in some ways, the advent of the CAD and MBD era challenges these assumptions that were formed many decades ago. When part definition is defined mathematically via a solid model, the assertion that one cannot interrogate the model, the direct analog of scaling the drawing, becomes ridiculous. Because when part definition is defined this way, it is not possible for a drawing or model to be not to scale. A 2D pencil drawing can be inaccurately foreshortened and skewed, and thus not to scale, yet still be a completely valid part definition as long as the labeled dimensions are the only dimensions used, and no scaling of the drawing by the user occurs. This is because what the drawing and labels convey is in reality a symbol of what is wanted, rather than a true replica of it. For example, a sketch of a hole that is clearly not round still accurately defines the part as having a true round hole, as long as the label says 10 mm DIA, because the DIA implicitly but objectively tells the user that the skewed drawn circle is a symbol representing a perfect circle. But if a mathematical model, essentially, a vector graphic, is declared to be the official definition of the part, then any amount of scaling the drawing can make sense. There may still be an error in the model, in the sense that what was intended is not depicted, modeled. But there can be no error of the not-to-scale type, because the mathematical vectors and curves are replicas, not symbols, of the part features. Even in dealing with 2D drawings, the manufacturing world has changed since the days when people paid attention to the scale ratio claimed on the print, or counted on its accuracy. In the past, prints were plotted on a plotter to exact scale ratios, and the user could know that a line on the drawing 15 mm long corresponded to a 30 mm part dimension because the drawing said 1-2 in the scale box of the title block. Today, in the era of ubiquitous desktop printing, where original drawings or scaled prints are often scanned on a scanner and saved as a PDF file, which is then printed at any % magnification that the user deems handy, such as fit to paper size, users have pretty much given up caring what scale ratio is claimed in the scale box of the title block. Which, under the rule of do not scale drawing, never really did that much for them anyway.
Showing dimensions.
The required sizes of features are conveyed through use of dimensions. Distances may be indicated with either of two standardized forms of dimension, linear and ordinate. With linear dimensions, two parallel lines, called extension lines, spaced at the distance between two features, are shown at each of the features. A line perpendicular to the extension lines, called a dimension line, with arrows at its endpoints, is shown between, and terminating at, the extension lines. The distance is indicated numerically at the midpoint of the dimension line either adjacent to it, or in a gap provided for it. With ordinate dimensions, one horizontal and one vertical extension line establish an origin for the entire view. The origin is identified with zeros placed at the ends of these extension lines. Distances along the x and y axes to other features are specified using other extension lines, with the distances indicated numerically at their ends. Sizes of circular features are indicated using either diametral or radial dimensions. Radial dimensions use and are followed by the value for the radius. Diametral dimensions use a circle with forward-leaning diagonal line through it, called the diameter symbol, followed by the value for the diameter. A radially aligned line with arrowhead pointing to the circular feature, called a leader, is used in conjunction with both diametral and radial dimensions. All types of dimensions are typically composed of two parts, the nominal value, which is the ideal size of the feature, and the tolerance, which specifies the amount that the value may vary above and below the nominal. Geometric dimensioning and tolerancing is a method of specifying the functional geometry of an object.
Sizes of drawings.
Sizes of the drawings typically comply with either of two different standards, ISO, World Standard, or ANSI ASME Y14, American, according to the following tables. The metric drawing sizes correspond to international paper sizes. These developed further refinements in the second half of the 20th century, when photocopying became cheap. Engineering drawings could be readily doubled, or halved, in size and put on the next larger, or, respectively, smaller, size of paper with no waste of space. And the metric technical pens were chosen in sizes so that one could add detail or drafting changes with a pen width changing by approximately a factor of the square root of 2. A full set of pens would have the following nib sizes: 0.13, 0.18, 0.25, 0.35, 0.5, 0.7, 1.0, 1.5 and 2.0 mm. However, the International Organization for Standardization, ISO, called for 4 pen widths and set a color code for each: 0.25, white, 0.35, yellow, 0.5, brown, 0.7, blue. These nibs produced lines that related to various text character heights and the ISO paper sizes. All ISO paper sizes have the same aspect ratio, 1 to the square root of 2, meaning that a document designed for any given size can be enlarged or reduced to any other size and will fit perfectly. Given this ease of changing sizes, it is of course common to copy or print a given document on different sizes of paper, especially within a series. For example, a drawing on A3 may be enlarged to A2 or reduced to A4. The U.S. customary A-size corresponds to letter size, and B-size corresponds to ledger, or tabloid size. There were also once British paper sizes, which went by names rather than alphanumeric designations. American Society of Mechanical Engineers, ASME, Y14.2, Y14.3, and Y14.5 are commonly referenced standards in the U.S.
Technical lettering.
Technical lettering is the process of forming letters, numerals, and other characters in technical drawing. It is used to describe, or provide detailed specifications for, an object. With the goals of legibility and uniformity, styles are standardized and lettering ability has little relationship to normal writing ability. Engineering drawings use a Gothic sans serif script, formed by a series of short strokes. Lowercase letters are rare in most drawings of machines. ISO lettering templates, designed for use with technical pens and pencils, and to suit ISO paper sizes, produce lettering characters to an international standard. The stroke thickness is related to the character height. For example, 2.5 mm high characters would have a stroke thickness, pen nib size, of 0.25 mm, 3.5 would use a 0.35 mm pen and so forth. The ISO character set, font, has a serifed 1, a barred 7, an open 4, 6, and 9, and a round-topped 3, that improves legibility when, for example, an AO drawing has been reduced to A1 or even A3, and perhaps enlarged back or reproduced faxed/microfilmed and C. When CAD drawings became more popular, especially using US-American software, such as AutoCAD, the nearest font to this ISO standard font was Romantic Simplex, Romans, a proprietary SHX font, with a manually adjusted width factor, override, to make it look as near to the ISO lettering for the drawing board. However, with the closed 4, and arced 6 and 9, Romans SHX typeface could be difficult to read in reductions. In more recent revisions of software packages, the TrueType font ISOCPR reliably reproduces the original drawing board lettering stencil style. However, many drawings have switched to the ubiquitous Arial TTF.
Conventional parts areas of an engineering drawing. Title block.
The title block, TB, is an area of the drawing that conveys header-type information about the drawing, such as drawing title, hence the name title block, drawing number, part number, S, name of the design activity, corporation, government agency, etc., identifying code of the design activity, such as a cage code, address of the design activity, such as city, state, province, country, measurement units of the drawing, for example, inches, millimeters, default tolerances for dimension callouts where no tolerance is specified, boilerplate callouts of general specs, intellectual property rights warning. Traditional locations for the title block are the bottom right, most commonly, or the top right or center.
Revisions block.
The revisions block, Rev block, is a tabulated list of the revisions, versions, of the drawing, documenting the revision control. Traditional locations for the revisions block are the top right, most commonly, or adjoining the title block in some way.
Effectivity block.
The effectivity block provides a, usually tabular, list of the effectivity of the part design, that is, which higher assemblies it is used in, and thus which models of machine the part is used in.
Notes list.
The notes list provides notes to the user of the drawing, conveying any information that the callouts within the field of the drawing did not. It may include general notes, flag notes, or a mixture of both. Traditional locations for the notes list are anywhere along the edges of the field of the drawing.
General notes.
General notes, GN, apply generally to the contents of the drawing, as opposed to applying only to certain part numbers or certain surfaces or features.
Flag notes.
Flag notes or flag notes, FL, FN, are notes that apply only where a flagged callout points, such as to particular surfaces, features, or part numbers. Typically the callout includes a flag icon. Some companies call such notes delta notes, and the note number is enclosed inside a triangular symbol, similar to capital letter delta, D. Floor 5, flag note 5, and D5, delta note 5, are typical ways to abbreviate in ASCII-only contexts.
Field of the drawing.
The field of the drawing, FD, is the main body or main area of the drawing, excluding the title block, rev block, and so on.
List of materials, bill of materials, parts list.
The list of materials, LM, low M, bill of materials, BM, BOM, or parts list, PL, is a, usually tabular, list of the materials used to make a part, and/or the parts used to make an assembly. It may contain instructions for heat treatment, finishing, and other processes, for each part number. Sometimes such low-miss or PLs are separate documents from the drawing itself. Traditional locations for the low M/BOM are above the title block, or in a separate document.
Parameter tabulations.
Some drawings call out dimensions with parameter names, that is, variables, such as A, B, C, then tabulate rows of parameter values for each part number. Traditional locations for parameter tables, when such tables are used, are floating near the edges of the field of the drawing, either near the title block or elsewhere along the edges of the field.
Views and sections.
Each view or section is a separate set of projections, occupying a contiguous portion of the field of the drawing. Usually views and sections are called out with cross-references to specific zones of the field.
Zones.
Often a drawing is divided into zones, with labels along the margins, such as A, B, C, D up the sides and 1, 2, 3, 4, 5, 6 along the top and bottom. Names of zones are thus, for example, A5, D2, or B1.
Abbreviations and symbols.
As in many technical fields, a wide array of abbreviations and symbols have been developed in engineering drawing during the 20th and 21st centuries. For example, cold-rolled steel is often abbreviated as CRS, and diameter is often abbreviated as DIA, D, or.
Example of an engineering drawing.
Here is an example of an engineering drawing, an isometric view of the same object as shown above. The different line types are colored for clarity. Black equals object line and hatching, red equals hidden line, blue equals center line of piece or opening, magenta equals phantom line or cutting plane line. Sectional views are indicated by the direction of arrows, as in the example right side.